Unveiling the mysteries of HTTP and HTTPS, secrets of the web revealed.
Hash Essentials series dive into the intricacies of HTTP and HTTPS, the mainstay protocols powering our daily web interactions. Today, we explore the structure of these protocols, detailing every component with real-world examples. We also demystify how browsers leverage TCP, not UDP, to ensure reliable, secure communication across the web, telling you about every possible header and its usage. Get ready to level up your understanding and perhaps be inspired by what makes the internet a fascinating world for development. However, keep in mind that this article is meant more as a reference on the topic, and reading it all at once might lead to severe boredom and depression, since it is more of an organized, condensed ChatGPT-4 communication than an article. HTTP and HTTPS, a tale of two protocols. HTTP Hypertext Transfer Protocol. HTTP is the lifeblood of the web, enabling the fetching and posting of HTML pages, images, and other vital resources. It follows a clear structure: 1. Start line describes the request type, the target resource, and the HTTP version. 2. Headers provide crucial metadata about the request or response. 3. Optional body contains data sent with methods like post or put. Example of an HTTP request: HTTPS secure HTTP. HTTPS adds a layer of TLS transport layer security to the traditional HTTP, enhancing the security by encrypting the transmitted data. It follows the same structural rules as HTTP but ensures that all transmitted data remains confidential and tamper-proof. Example of an HTTPS request: browser communication connecting through TCP. The role of TCP in HTTP/HTTPS. When a browser needs to fetch a web page or send data to a server, it uses TCP, the dependable delivery guy of the internet. TCP ensures that all packets arrive in the right order and none are lost, which is crucial for successfully rendering web pages. Communication timeline: TCP connection establishment, three-way handshake *SYN. The client sends a synchronized SYN packet to the server to initiate a connection. *SYNEC. The server responds with a synchronized acknowledge SYN ACK. *ACK. The client sends an acknowledge ACK, and the connection is established. Data transmission *. After the handshake, the client sends the HTTP/HTTPS request through the established TCP connection. *. The server processes the request and sends back an HTTP/HTTPS response, segmented and managed by TCP. Connection termination *. Once the session is complete, either side can initiate a connection termination. This involves another handshake using FIN finish and ACK packets to gracefully close the connection. Why not UDP? UDP, known for its speed in scenarios like live broadcasts or gaming, lacks the reliability mechanisms inherent to TCP. For web transactions where data integrity and order are paramount, TCP's ability to manage sequence and acknowledge receipt of packets makes it indispensable. Mastering HTTP methods are GET, POST, and beyond HTTP methods are a critical part of the web's operational fabric, defining the action to be performed on a given resource. Each method has specific use cases and implications for data security and idempotency. Let's dive into the details of these methods, particularly focusing on GET and POST, and then expanding to cover others like PUT, DELETE, and patch. GET method purpose: the GET method is used to retrieve information from the specified server using a given URI. Requests using it should only retrieve data and should have no other effect on the data. Example: key points: idempotent and safe. GET requests are both idempotent and safe, meaning issuing the same GET request multiple times will always produce the same result, and they do not modify resources. Data in URL: all required data is sent in the URL, including query parameters, which makes it limited in length and less secure. Cache and GET requests are cacheable, which means they can be stored in a cache to speed up repeated requests to the same resource. POST method purpose: the POST method is used to submit data to the server, such as customer information, file uploads, or messages. It is typically used when a resource,
needs to be created or updated. Example: key points : not idempotent. Post requests are not idempotent, which means submitting the same post request multiple times can result in different outcomes or side effects. Node data limitation: unlike GET, POST does not have size limitations and can include data in the body of the request, making it more secure for sensitive data. Less cacheable: POST responses are not usually cacheable by default unless response headers explicitly allow it. Other HTTP methods this method is used for updating or replacing a resource entirely. It is idempotent, meaning that multiple, identical put requests should have the same effect as a single request. Example: delete. The delete method removes the specified resource. It is also idempotent, which ensures that the result of deleting a resource is the same no matter how many times it is executed. Example: patch used for making partial changes to a resource.
Patch is neither safe nor idempotent, but can be more efficient than put as it only sends updates for the changes rather than the whole resource. Example: implementing HTTP methods in Node.js and PHP. To give you a real-world grasp on these methods, here's how you can implement them in server-side programming using Node.js and PHP: Node.js with ExpressPHP using simple routing mechanism, URL structure, and components. A URL uniform resource locator is a reference to a web resource.
Let's break down its structure. 1. Scheme: indicates the protocol HTTP or HTTPS. 2.
Host: the domain name or IP address of the server. 3.
Port: optional specifies the port number.
4.
Path: specifies the specific resource or endpoint.
5. Query: optional provides additional parameters. 6.
Fragment: optional directs to a specific part of the resource. HTTP headers: building blocks of HTTP request. HTTP headers are a fundamental aspect of web development, allowing developers to control how browsers and servers communicate.
They can dictate everything from client-server interactions to instructions for caching and how requests/responses should be handled.
Let's explore each of these headers in detail, understanding their purpose and seeing how they are implemented in different programming environments and server configurations. Request headers: request headers are part of the HTTP protocol, which stands for Hypertext Transfer Protocol. When a client, such as a web browser, makes a request to a server, it sends an HTTP request. This request consists of 3 main parts: the request line, the request headers, and the body.
The headers are key value pairs that provide additional context about the request. Think of request headers as the courier's node attached to a package.
They convey important details such as who the package is from, what's inside, how it should be handled, and how the recipient should respond.
General request headers: general request headers provide essential context for HTTP requests, shaping how data is transferred between the client and server.
These headers, such as inform the server about the client's capabilities and preferences, such as the types of content it can handle or the browser it's using. By leveraging general request headers, servers can tailor responses to better suit the client's needs, ensuring a more efficient and optimized interaction. Cache control: the header is used to specify directives for caching mechanisms in both requests and responses.
It defines how and for how long the content can be cached. It is used to control how responses are cached by browsers and intermediate caches. Connection: the header controls whether the network connection stays open after the current transaction finishes. Its values include keep, live, or close. It is used to control the network connection behavior. Date: the header represents the date and time at which the message was originated. This header can be used by the server for logging and to validate the request. It is used to indicate the date and time when the message was sent. Primer: the header is a general header that is used for backwards compatibility with HTTP/1.0 caches where it allows the client to request specific caching behavior. It is used to control caching mechanisms. Via: a header is used to track the intermediaries proxies through which the request passes. It is used for debugging and tracing the request path. It is used to specify the intermediate proxies involved in the request. Warning: the header carries additional information about the status or transformation of a message that might not be reflected in the response status code. It is used to convey warnings to the user.
Client-specific headers. Client-specific headers are designed to offer detailed insights into the client's environment and requirements.
For instance, headers like can indicate if the request is coming from a specific application or provide unique identifiers for the client. These headers are crucial for personalization and for implementing features such as analytics or targeted content, allowing servers to respond in ways that are optimized for each particular client. From the header contains an internet email address for a human user who controls the requesting user agent. This is used for logging purposes and should not be used for unsolicited emails. It is used to indicate the email address of the user making the request. Refer: the header indicates the address of the previous web page from which a request was made. It is used for analytics and logging purposes. It is used to specify the URL of the referring page. User agent: the header contains a string that identifies the user agent browser application making the request. This is used for content negotiation and analytics. It is used to identify the client software initiating the request. XATT device ID: the header is used to pass the AT&T device identifier, often used for tracking and identification purposes, by AT&T. It is used to pass the AT&T device identifier. The AT&T device identifier is a unique identifier assigned to each device connected to the AT&T network. It's used primarily for tracking, managing, and identifying devices. XWAP profile: the header is used to link to a WAP profile for the client device. This profile contains device capabilities and configurations. It is used to specify the URL of the device's WAP profile. A WAP wireless application protocol profile is essentially a set of specifications that describe the capabilities and configuration of a mobile device for the purposes of accessing WAP content.
Think of it as a device profile that tells servers what features and limitations the device has, so the server can tailor content accordingly.
Conditional headers: conditional headers play a pivotal role in optimizing resource usage and ensuring data consistency.
Headers like allow clients to request resources only if they have changed since the last access.
This helps to minimize unnecessary data transfers and server load, enhancing performance and making the web experience more efficient by leveraging caching mechanisms and reducing bandwidth consumption. If match: the header makes the request conditional by requiring the entity tag etag to match one of the listed values.
If none of the tags match, a 412 precondition failed response is returned. It is used to make a request conditional based on etag. An etag, or entity tag, is an HTTP header used for web cache validation and conditional requests.
It is a mechanism that helps manage the state of resources and improve the efficiency of web interactions. If modified: since the header makes the request conditional by requesting the resource only if it has been modified since the specified date and time. It is used to make a request conditional based on modification time. If non-match: the header makes the request conditional by requesting the resource only if the etag does not match any of the listed values. It is often used to update cache data. It is used to make a request conditional based on etag. If range: the header makes the request conditional by requesting the resource only if it has not been modified since the specified date or etag. It is often used with range requests. It is used to make a range request conditional based on etag or modification time. If modified: since the header makes the request conditional by requesting the resource only if it has not been modified since the specified date.
It is often used to prevent lost updates. It is used to make a request conditional based on modification time. Content headers: content headers are essential for defining the nature and format of the data being sent or received.
Headers such as and inform the recipient about the type of content, e.g.,
JSON, HTML, and its size, which is crucial for proper data handling and rendering. These headers ensure that the data is correctly interpreted and processed, maintaining the integrity and usability of the content across different platforms, and devices.content length. The header indicates the size of the request body in bytes. This header is required in HTTP/1.1 for any request that contains a body. It is used to specify the size of the request body. Content MD5. The header provides an MD5 hash of the request body, ensuring the integrity and authenticity of the content, allowing the receiver to verify the body has not been altered. It is used to verify the integrity of the message body. Content type. The header indicates the media type of the resource or the data being sent in the body of the HTTP request.
Common values including .it is used to specify the media type of the request body.
Authentication headers. Authentication headers are critical for securing interactions between clients and servers.
Headers can facilitate the exchange of credentials, ensuring that only authorized users can access protected resources. This layer of security is fundamental in safeguarding sensitive information and maintaining the privacy and integrity of user data within web applications and services. Authorization. The header is used to send credentials to authenticate a user agent with a server.
This header often includes tokens, passwords, or other forms of authentication. It is used to pass authentication information. Proxy authorization. The header is used to send credentials to a proxy server, allowing the client to authenticate itself with the proxy. It is used to pass authentication information to a proxy.
CARS headers. Cross-origin resource sharing. CARS headers manage how resources are shared across different origins, addressing cross-origin requests with fine-tuned control.
Headers such as SAND are used to specify which domains can access resources and what HTTP methods are allowed.
This mechanism is vital for enabling secure and controlled interactions between web applications hosted on different domains, preventing unauthorized access while facilitating necessary integrations. Access control request method. The header is used in CARS per flight requests to let the server know which HTTP method will be used when the actual request is made. It is used to specify the method for a CARS request. Access control request headers. The header is used in CARS per flight requests to indicate which HTTP headers will be used when the actual request is made. It is used to specify the headers for a CARS request. Origin. The header indicates the origin scheme, host, and port of the request. It is used by the server to determine whether or not to allow the request. Especially in CARS requests. It is used to specify the origin of the request. Custom headers. Cookie.
The header is used to send cookies from the client to the server. Cookies are often used for session management, tracking, and personalizing user experiences. It is used to pass cookies to the server. Accept. The header informs the server about the types of media that the client can process, such as HTML, JSON, XML, etc. This helps the server to send a response in a format that the client understands. It is used to specify the media type S that are acceptable for the response. Accept charset. The header indicates the character sets that the client is able to understand.
This can help ensure that the content is correctly encoded. It is used to specify the preferred character sets for the response. Accept encoding. The header advertises which content encoding the client can understand, such as gzip, deflate, or bar. This allows the server to send compressed content. It is used to specify the acceptable content encoding methods. Accept language. A header is used to specify the preferred languages for the response. This is particularly useful for serving content in the user's preferred language. It is used to specify the preferred languages for the response. Accept at a time. The header is used to make a request for a specific version of a resource, as it existed at a particular point in time. It is used to request a specific version of a resource based on data time. Expect. The header is used to indicate that particular server behaviors are required by the client.
For example, it can be used to request a response before sending a large body. It is used to specify expectations that must be met by the server. Forwarded. The header is used to disclose information about the client and the proxy servers involved in the request. It standardizes the format of these details. It is used to pass on the details of the original client and proxy chain. Host. The header specifies the domain name of the server and the TCP port number on which the server is listening. is mandatory in HTTP/1.1 requests. It is used to specify the domain name and port of the server. Max forwards. The header provides a mechanism with the trace and options methods to limit the number of times the request is forwarded by proxies. It is used to limit the number of times a request is forwarded. Range. The header is used to request a specific range of bytes from a resource. It is commonly used to resume interrupted downloads or to stream media. It is used to specify the byte range to fetch from a resource. The header indicates the transfer encodings the client is willing to accept, such as chunked.
It is used to specify acceptable transfer encodings. It is used to specify the transfer encodings the client can handle. Upgrade.
Idiocracy. The header is used to request the server to switch protocols, such as switching from HTTP/1.1 to WebSocket. It is used to request an upgrade to a different protocol. X requested with the header is commonly used to identify AJAX requests.
Most JavaScript frameworks send this header with the value. It is used to indicate that the request was made via AJAX.dnt. The do not track header is used to request that a web application disable either its tracking or cross-site user tracking of an individual user. It is used to indicate the user's tracking preference. X forwarded for the header is used to identify the originating IP address of a client connecting to a web server through a proxy or load balancer. It is used to pass the original client's IP address. X forwarded host. The header is used to specify the original host requested by the client in the HTTP request header. It is used to pass the original host requested by the client. X forwarded proto. The header is used to indicate the protocol HTTP or HTTPS that a client used to connect to the proxy or load balancer. It is used to pass the protocol used by the client. Front end HTTPS. The header is used by Microsoft applications to indicate that the front end is using HTTPS. It is used to specify that the front end is using HTTPS.x HTTP method override. The header is used to override the HTTP method. This is useful when the client or server only supports GET and POST methods, but the application needs to use other methods like put or delete. It is used to override the HTTP method specified in the request.prox connection. The header is a non-standard header used to control the connection behavior between a client and a proxy server. Similar to the header. It is used to control the proxy connection behavior. X2. The header is used by Verizon Wireless to insert a unique identifier header into HTTP requests, often used for tracking and advertising purposes. It is used to pass the unique identifier header. X CSRF token. The header is used to prevent cross-site request forgery CSRF attacks by ensuring that the request is coming from a trusted source. It is used to pass the CSRF token for security purposes. X request ID. The header is used to uniquely identify an HTTP request, often used for tracking and logging purposes. It is used to pass a unique identifier for the request. X correlation ID. The header is used to correlate HTTP requests and responses between clients and servers, often used for tracing and debugging in distributed systems. It is used to pass a correlation identifier for tracking purposes. X frame options. The header is used to control whether a browser should be allowed to render a page in A or
This helps to prevent click-checking attacks. It is used to specify whether the page can be displayed in a frame. Response headers. When a server responds to a client's request, it sends back an HTTP response consisting of three main parts: the status line, the response headers, and the body.
The response headers are key value pairs that provide additional information about the server's response. Think of response headers as the detailed report accompanying a delivered package.
They communicate critical information about the response, such as the type of content being delivered, the encoding format, security policies, and any cookies that need to be set.
These headers ensure that the client knows how to properly handle and interpret the incoming data, enhancing the efficiency and security of web communication. General response headers. General response headers provide fundamental information about the server's response, shaping how clients interpret and handle the received data.
Headers like and offer insights into the server's identity and the timestamp of the response, respectively.
These headers help clients understand the context of the response and make informed decisions, such as when to refresh or reprocess the information. Date the header represents the date and time at which the message was originated. This header can be used by the server for logging and to validate the request. It is used to indicate the date and time when the message was sent. Connection. The header controls whether the network connection stays open after the current transaction finishes. Its values include keep alive or close. It is used to control the network connection behavior. Via. The header is used to track the intermediaries proxies through which the request passes. It is used for debugging and tracing the request path. It is used to specify the intermediate proxies involved in the request. Warning. The header carries additional information about the status or transformation of a message that might not be reflected in the response status code. It is used to convey warnings to the user.
Entity headers. Entity headers deliver details about the resource being transmitted, such as its length, type, and encoding. Headers like "and" are crucial for the client to properly interpret and display the resource. By providing this metadata, entity headers ensure that the data is processed correctly and enhances the compatibility of the content across various systems and applications. Allow the header lists the set of HTTP methods supported by a resource.
This is used in responses to indicate which methods are allowed. It is used to specify the allowed HTTP methods for a resource. Content disposition. The header provides information about how the content should be displayed, often used to indicate if the content should be displayed inline or as an attachment. It is used to specify how content should be displayed or downloaded. Content encoding. The header is used to specify the encoding transformations that have been applied to the body of the response, such as gzip or deflate. It is used to specify the encoding of the response body. Content language. The header is used to describe the language as intended for the audience of the response body. It is used to specify the language of the response content. Content location. The header is used to specify an alternate location for the return data, useful for indicating the location of a resource. It is used to specify the URI where the resource can be found. Content range. A header is used to specify the range of bytes that the server is returning, useful for resuming downloads and handling partial content requests. It is used to specify the range of the response body. E-tag. The header provides the current value of the entity tag for the requested variant. This value is used for caching and conditional requests. It is used to specify the e-tag of the resource. Expires. The header gives the date and time after which the response is considered stale. It is used to control caching. It is used to specify the expiration time for the response. Last modified. The header indicates the date and time at which the resource was last modified.
This can be used for caching and conditional requests. It is used to specify the last modification time of the resource.
Content headers. Content headers are integral to defining and managing the specifics of the data within the response.
Headers such as dictate how the content should be handled by the client, whether it's to be displayed inline, downloaded, or treated in a particular manner.
These headers play a key role in content presentation and user experience by ensuring that the data is properly formatted and managed. Content length. The header indicates the size of the request body in bytes.
This header is required in HTTP/1.1 for any request that contains a body. It is used to specify the size of the request body. Content type. The header indicates the media type of the resource or the data being sent in the body of the HTTP request.
Common values including. It is used to specify the media type of the request body.
Caching headers. Caching headers control how and when responses are stored and reused by clients in intermediate caches. Headers like and provide directives for caching mechanisms, determining the duration and conditions under which cache data is considered valid.
Effective use of caching headers improves performance and reduces server load by minimizing redundant data retrieval and leveraging previously fetched resources. Cache control. The header is used to specify directives for caching mechanisms in both requests and responses.
It defines how and for how long the content can be cached. It is used to control how responses are cached by browsers and intermediate caches. Expires. The header gives the date and time after which the response is considered stale.
It is used to control caching. It is used to specify the expiration time for the response. Last modified. The header indicates the date and time at which the resource was last modified. This can be used for caching and conditional requests. It is used to specify the last modification time of the resource. E tag the header provides the current value of the entity tag for the requested variant. This value is used for caching and conditional requests. It is used to specify the E tag of the resource. Redirect headers. Redirect headers are used to guide clients to a different URL when the requested resource has moved or requires redirection.
Headers such as and status codes like current from the client of the new resource location.
Redirect headers are essential for managing URL changes, maintaining link integrity, and ensuring that users are directed to the correct resources or updated locations. Location. The header is used to redirect the recipient to a location other than the request URL, often used in redirection or after resource creation. It is used to specify the URL to redirect. Refresh. The header is used to instruct the client to refresh the page after a specified number of seconds. It is used to specify the refresh interval for the client. Retry. After the header indicates how long the user agent should wait before making a follow-up request. Used in responses with status 500 pre-service unavailable. It is used to specify when the client can retry the request. Authentication headers. Authentication headers are critical for verifying the identity of clients requesting access to protected resources. Headers can facilitate the exchange of credentials, such as tokens or API keys, to authenticate users or applications. These headers play a crucial role in securing access to sensitive information and ensuring that only authorized entities can interact with protected endpoints. Www authenticate. The header is used in responses to indicate that the client must authenticate itself to get the requested response. It is used in conjunction with 401 unauthorized status codes. It is used to specify the authentication scheme and parameters. Proxy authenticate. The header is used by a proxy server to challenge the client for authentication credentials. This header is included in a response, indicating that the client must authenticate itself with the proxy. It is used to specify the authentication method that should be used to access a resource behind a proxy. Security headers. Security headers are vital for enhancing the security posture of web applications by providing protection against common threats. Headers like and help mitigate risks such as cross-site scripting, XSS, click-checking, and man-in-the-middle attacks. Implementing these headers strengthens the security of web interactions and safeguards both user data and application integrity. Strict transport security. The header HTTPS is used to enforce secure HTTPS connections to the server. It can prevent protocol downgrade attacks and cookie hijacking. It is used to enforce HTTPS connections. X-frame options. The header is used to control whether a browser should be allowed to render a page in a This helps to prevent click-checking attacks. It is used to specify whether the page can be displayed in a frame. X content type options. The header is used to prevent browsers from interpreting files as a different MIME type to what is specified in the header. A common value is. It is used to prevent MIME type sniffing. XSS protection. The header is used to enable or disable the cross-site scripting XSS filter built into most web browsers. A common value is. It is used to control the XSS protection mechanism in the browser. Custom headers link. The header provides a means for serializing one or more links in HTTP headers, useful for indicating relationships like pagination links. It is used to provide relational links in the response. P3P. The header is a way of making privacy policies available to user agents. It's used to apply privacy preferences automatically. It is used to provide a privacy policy for the response. Server. The header contains information about the software used by the origin server to handle the request. This can include details like the name and version of the software. It is used to identify the server software. Set cookie. The header is used to send cookies from the server to the user agent. The client then includes these cookies in subsequent requests to the server. It is used to set cookies on the client. Transfer encoding. The header specifies the form of encoding used to safely transfer the payload body to the user. It can include values like. It is used to specify the encoding used to transfer the response body. Upgrade and secure requests. The header is sent by the client to indicate that it can handle secure HTTPS responses for the same URL typically used to request HTTPS content over HTTP. It is used to indicate the client supports upgrading to HTTPS. Vary. The header is used to indicate that the response varies based on the value of specified request headers. This is used for content negotiation, and caching. It is used to specify the headers that influence the response content. X powered by the header indicates the technology used by the web server.
It is often used to identify the backend technology. It is used to indicate the technology stack of the server. XUA compatible. The header is used to specify the document modes for Internet Explorer. It helps to control the behavior of the browser. It is used to specify the document mode for Internet Explorer. HTTP/HTTPS protocol details. The HTTP Hypertext Transfer Protocol and HTTPS HTTP Secure protocols have been the backbone of web communication since their inception. HTTP was introduced in 1991 by Tim Berners-Lee, evolving rapidly to address the growing needs of the web. HTTP/1.1, standardized in 1997, brought persistent connections and chunk transfer encoding, enhancing performance and efficiency. As security became a priority, HTTPS emerged, incorporating SSL/TLS encryption to safeguard data in transit. The introduction of HTTP/2 in 2015 marked a significant leap, introducing multiplexing, header compression, and server push to improve speed and resource utilization. Looking ahead, HTTP/3 built on quick promises even faster, more reliable connections by reducing latency and improving security. The evolution of HTTP/HTTPS continues to focus on performance, security, and adaptability to meet the demands of modern web applications. HTTP/1.0 release year 1996 key features: simple, stateless protocol. Each request opens a new connection, leading to inefficiencies. Limited to basic request methods get, post, head. HTTP/1.1 release year 1997 key features: persistent connections keep alive. Chunk transfers for dynamic content.
Better caching mechanisms. Additional request methods like put, delete, options, trace. HTTP/2 release year 2015 key features: binary protocol for improved performance. Multiplexing multiple requests over a single connection.
Header compression to reduce overhead. Server push to proactively send resources to clients. HTTP/3 release year 2020 draft key features: based on quick protocol built on UDP.
Reduced latency for faster load times.
Improved security and reliability. HTTP/2 and HTTP/3 improvements. HTTP/2 binary protocol. Unlike its predecessor, HTTP/2 uses a binary format instead of text, which significantly reduces the complexity of parsing. Multiplexing. HTTP/2 can send multiple requests for data in parallel over a single TCP connection, thereby reducing latency and improving page load times. Header compression. HTTP/2 introduces HBAC, a header compression algorithm that reduces the overhead of HTTP headers, speeding up data transfer. Server push. This feature allows servers to send resources to the client proactively, without the client explicitly requesting them. It can significantly improve load times for web pages by reducing the number of round trips needed to fetch resources. HTTP/3 built on Quick. HTTP/3 is based on the Quick protocol, which uses UDP instead of TCP.
This change reduces the latency that comes with TCP's connection establishment and congestion control mechanisms. Reduced latency. Quick connection establishment requires fewer round trips compared to TCP, which results in faster initial page loads. Improved security. Quick integrates TLS 1.3, ensuring that all connections are encrypted by default, enhancing security, while also improving performance by reducing the time needed to establish a secure connection. Resilience to packet loss. Unlike TCP, which experiences delays with packet loss, Quick design allows for faster recovery and less impact on overall connection performance.
Connection Keep Alive Persistent connections. The Keep Alive mechanism allows a single TCP connection to stay open for multiple HTTP requests/responses, reducing the overhead of setting up new connections for each request.
This is crucial for improving the performance of web applications by reducing latency. Reduced latency. By maintaining open connections, Keep Alive eliminates the need for repeated TCP handshakes, which can significantly reduce latency for successive requests. Resource efficiency. It helps in reducing the load on both client and server resources by limiting the number of open connections at any given time. Configuration. Keep Alive settings can be fine-tuned, for example timeout duration, maximum requests, to optimize performance based on specific application needs and server capacities. Persistent connections definition. Persistent connections refer to the practice of reusing a single connection to send and receive multiple HTTP requests/responses instead of opening a new connection for every single transaction. Efficiency. This reuse of connections greatly enhances efficiency by reducing the overhead associated with opening and closing connections frequently. Connection management. Persistent connections are managed through HTTP headers which instruct the server to keep the connection open. Load handling. They help in better handling high loads by minimizing the time and resources spent on connection management, thus allowing servers to serve more requests simultaneously.
Chunk transfer encoding purpose. Chunk transfer encoding is used to send data in a series of chunks. This is particularly useful for sending dynamically generated content where the total content length is unknown at the start of the transmission. Implementation. With chunk transfer encoding, each chunk is preceded by its size in bytes, and the transmission ends with a zero-size chunk. Benefits: dynamic content, ideal for streaming large files or dynamically generated content where the total size is unknown until the end.
Memory efficiency helps in reducing memory usage on the server side as data can be sent as it is generated rather than buffering the entire content.
Compatibility supported by HTTP/1.1 and later versions, making it a robust solution for various applications. Use cases. Chunk transfer encoding is commonly used in APIs, video streaming, and any application requiring real-time data transmission. Caching in HTTP protocols. Caching is a crucial aspect of web performance optimization.
It helps in reducing latency, bandwidth consumption, and server load by storing copies of resources and reusing them for subsequent requests.
Here are some key HTTP headers used to control caching behavior. Cache control header definition. The header is used to specify directives for caching mechanisms in both requests and responses. Common directives: public indicates that the response can be stored by any cache, even if it is normally non-cacheable. Private indicates that the response is intended for a single user and should not be stored by shared caches.
No cache forces caches to submit the request to the origin server for validation before releasing a cached copy.
No store instructs caches to not store any part of the request or response. Max age equals seconds specifies the maximum amount of time a resource is considered fresh.
After this time, the cache must revalidate the resource.
S maxage equals seconds, similar to but specifically for shared caches, e.g.
CDN. Use cases: static content long to reduce load on origin servers.
Dynamic content use auto ensure the content is always validated. Expires header definition. The header specifies a date/time after which the response is considered stale.
It provides an absolute expiration time in the HTTP date format. Behavior: static content setting a future date for resources that do not change often. Dynamic content use a date that ensures frequent validation with the server. Example: considerations: is less flexible compared to SAN, can lead to issues if the client and server clocks are not synchronized.
Tag header definition. The entity tag header is used for resource versioning.
It acts as a unique identifier for a specific version of a resource. Functionality: validation. Clients can use the header with an E tag to check if the cached version matches the server's current version.
Asterisk conditional requests. If the E tag matches, the server can respond with a status. Saving bandwidth. Usage: ** static files generate E tags based on file content or a hash of the file. * dynamic content E tags can be based on a content version identifier from the database.
Last modified header definition. The header indicates the date and time at which the origin server believes the resource was last modified. Usage: ** validation. Clients can use the header to check if the resource has been modified since the specified date. * conditional requests. If the resource has not been modified, the server can respond with .example: considerations: * best used when the modification date is reliable and reflects actual content changes. Vary header definition. The header is used to indicate which headers a cache should use to determine whether a cached response is fresh. Common directives: * vary except encoding indicates that the response varies based on the header, for example gzip, deflate. * vary user agent indicates that the response varies based on the header. Usage: * ensures that caches correctly handle responses that vary based on certain request headers, preventing incorrect or stale responses from being served. Example: considerations: * the header can significantly impact cache efficiency and should be used judiciously.
Authentication and authorization in HTTP. Authentication and authorization are critical components of web security. They ensure that users are who they claim to be. Authentication and that they have the necessary permissions to access resources. Authorization. Here's a breakdown of various methods and their typical HTTP requests/responses, along with popular libraries for different frameworks. Basic authentication description. Basic authentication is a simple authentication scheme built into the HTTP protocol.
It uses a base 64 encoded string of the formats int and the header. HTTP request, HTTP response. Popular libraries: Node.js: PHP: built-in PHP functions with and open/closed source solutions: Apache *Nginx: digest authentication description. Digest authentication is more secure than basic authentication. It uses a challenge response mechanism to avoid sending passwords in plaintext. HTTP request, HTTP response. Popular libraries: Node.js: PHP: built-in PHP functions with open/closed source solutions: Apache *Nginx: OAuth description. OAuth is an open standard for access validation. It allows users to grant third-party applications access to their resources without sharing their credentials. HTTP request authorization code grant HTTP response access token. Popular libraries: Node.js: PHP: open/closed source solutions: Auth0 closed source *Keycloak open source token-based authentication description. Token-based authentication involves generating a token after a successful login, which is then used for subsequent requests. HTTP request, HTTP response token generation. Popular libraries: Node.js: PHP: open/closed source solutions: Auth0 closed source *JWT.io open source tools. JWT JSON web tokens description. JWT is a compact, URL-safe means of representing claims to be transferred between two parties. It's commonly used for authorization. HTTP request with JWT. HTTP response. Popular libraries: Node.js: PHP: open/closed source solutions: Auth0 closed source *Keycloak open source. Cookies and sessions. Cookies and sessions are fundamental to maintaining state in web applications. They allow web servers to store and retrieve data on the client's side, enabling functionalities like user authentication, preferences, and shopping carts. Setting and managing cookies. Setting cookies. Cookies are small pieces of data stored on the client side and sent to the server with each request. They are set using the HTTP header.node.js example :PHP example secure, and HTTP only flags secure flag. The flag ensures that the cookie is only sent over HTTPS, providing a layer of security by preventing cookie theft during transmission. HTTP only flag theft prevents JavaScript from accessing the cookie, mitigating the risk of cross-site scripting. XSS attacks. Node.js example :PHP example session management sessions provide a way to store data across multiple requests. They are typically stored on the server, with a session ID sent to the client via a cookie. Node.js example using PHP example using native session handling. By utilizing cookies and sessions effectively, you can maintain state across multiple client-server interactions, providing a seamless and personalized user experience. Secure flags and session management are essential for ensuring the security and integrity of your web applications.
Happy coding.
Proxies and reverse proxies. Forward proxy. A forward proxy acts as an intermediary between a client and the Internet. It can be used to mask the client's IP address, filter requests, and cache responses to improve performance. Forward proxies are typically used for : anonymity, hiding the client's IP address, * content filtering, blocking access to certain websites, * caching, storing frequently accessed content to reduce bandwidth usage. Reverse proxy. A reverse proxy sits between the client and the server, forwarding client requests to the appropriate backend server.
It is used to : load balancing, distributing client requests across multiple servers.
* caching, storing responses from the backend server to reduce load. * SSL termination, handling SSL encryption/decryption to offload this task from the backend server. * security, protecting the backend server by hiding its IP address and providing an additional layer of security. Proxy headers. Forwarded for the header is used to identify the originating IP address of a client connecting to a web server through a proxy or load balancer. It contains a comma-separated list of IP addresses, where the first IP is the client's IP, and subsequent IPs are those of proxy servers. Forwarded host. The header indicates the original host requested by the client in the HTTP header. This is useful for maintaining the original host information when requests pass through a reverse proxy. Setting up proxies with Apache, Nginx, PHP, and Node.js on Ubuntu server. Apache forward proxy configuration: install Apache if not already installed, enable the necessary modules, configure the forward proxy, and restart Apache, reverse proxy configuration: install Apache if not already installed, enable the necessary modules, configure the reverse proxy, and restart Apache, Nginx forward proxy configuration: install Nginx if not already installed, configure the forward proxy, and restart Nginx, reverse proxy configuration: install Nginx if not already installed, configure the reverse proxy, and restart Nginx. PHP. When using PHP behind a proxy, you need to correctly handle proxy headers. For example, to get the real client's IP address, you can use Node.js, creating a basic reverse proxy: install package: create a reverse proxy server: run the Node.js server: by setting up proxies and reverse proxies, you can enhance the performance, security, and scalability of your web applications.
Using Apache, Nginx, PHP, and Node.js, you have a versatile set of tools to manage and optimize your server's traffic efficiently. Compression in web servers. Content encoding: the header is used by the server to indicate the type of compression used on the response data. Common compression methods include : gzip, one of the most widely supported and used compression methods. It offers a good balance between compression ratio and speed.
*deflate, another widely supported method that uses the zlib data format.
It's less common than gzip but still used. *bar, broadly a newer compression algorithm developed by Google.
It offers a higher compression ratio compared to gzip and deflate, but it's not as universally supported by older browsers. Accept encoding header: the header is sent by the client to indicate which content encoding methods it supports. The server then uses this information to choose an appropriate encoding method for the response. Example of auto setting up compression on Ubuntu server with Apache and Nginx Apache install Apache enable for gzip and deflate compression enable for abruptly compression if available configure compression edit the configuration file typically located at to include the following settings for gzip and deflate for abruptly restart Apache Nginx install Nginx configure compression edit the Nginx configuration file typically located at to include the following settings install Brotli module if Brotli is not already included in your Nginx build you may need to install it. For example, restart Nginx advanced topics in web development. WebSockets provide a full duplex communication channel over a single, long-lived connection. This allows for real-time data exchange between a client and server, making it ideal for applications like chat apps, live notifications, and online gaming. Key features full duplex communication. Both the client and server can send and receive messages simultaneously. Persistent connection reduces the overhead of establishing multiple HTTP connections. Low latency enables real-time communication with minimal delay. Typical use cases real-time chat applications live sports updates online multiplayer games collaborative editing tools server-sent events server-sent events allow a server to push updates to the client over a single HTTP connection.
Unlike WebSockets, SSE is a unidirectional protocol where data flows from the server to the client. Key features simple API SSE uses regular HTTP and can be handled with standard web server configurations. Automatic reconnection built-in support for automatic reconnection and event ID tracking. Text-based protocol SSE transmits data as text, making it easy to debug and understand. Typical use cases live news feeds real-time notifications streaming stock prices social media updates HTTP/2 server push HTTP/2 server push allows the server to send resources to the client before the client explicitly requests them. This can significantly reduce page load times by proactively delivering content that the server knows the client will need. Key features proactive resource delivery sends resources that are likely to be needed by the client, reducing latency. Single connection uses the same connection for multiple streams, improving efficiency. Improved performance reduces the number of round trips required to fetch resources. Typical use cases delivering style sheets and scripts alongside the main HTML document. Preloading images and other assets for improved user experience. HTTP pipelining allows multiple HTTP requests to be sent out before the responses are received. This can improve the performance of HTTP/1.1 connections by reducing the latency associated with waiting for each response before sending the next request. Key features sequential requests. Requests are sent in sequence without waiting for the corresponding responses. Potential latency reduction can reduce latency by overlapping request and response transmission. Challenges head of line blocking. If one request takes a long time, it can block subsequent requests. Limited browser support due to issues like head-of-line blocking. Many browsers have limited or no support for pipelining. Testing and tools for HTTP protocol testing and debugging HTTP requests are vital aspects of web development. Various tools can help you inspect, test, and debug HTTP traffic efficiently. Here's an overview of some essential tools and techniques. Using CURL for HTTP requests. CURL is a powerful command line tool that allows you to send HTTP requests and interact with web servers. It supports various protocols, including HTTP, HTTPS, and FTP, making it a versatile tool for developers. With CURL, you can customize requests by specifying headers, data, authentication, and other parameters. It's particularly useful for testing REST-file APIs, downloading files, and sending post requests with data payloads. Additionally, See URL's detailed output options are invaluable for debugging HTTP requests. Postman for API testing. Postman is a widely used GUI tool for testing APIs, providing a user-friendly interface to send HTTP requests, inspect responses, and automate testing workflows. It allows you to construct GET, POST, PUT, DELETE, and other HTTP requests with ease. Postman enables you to organize and save API requests into collections, making it simple to reuse and share them with your team. With its built-in JavaScript testing capabilities, you can write tests to automate API testing and validate responses. Managing different environments with variables is another feature that makes Postman ideal for testing APIs across multiple settings. Browser developer tools for inspecting HTTP traffic. Modern browsers come equipped with developer tools that are essential for inspecting and debugging HTTP traffic. The network panel allows you to view all HTTP requests made by a web page, including request and response headers, payloads, and timing information. The console lets you execute JavaScript code, log messages, and debug scripts, while the application panel provides access to cookies, local storage, and session storage. These tools are crucial for analyzing network performance, identifying bottlenecks, and managing browser storage effectively. Network monitoring tools. Network monitoring tools offer deeper insights into network traffic and performance. They help identify issues at a lower level, such as network latency, packet loss, and server performance. Tools let Wireshark capture and display network traffic in real time, allowing for detailed traffic analysis. Nagios and Zabbix provide comprehensive network monitoring and alerting capabilities, helping you diagnose network issues, monitor server and application performance, and analyze security vulnerabilities. These tools are essential for maintaining optimal network performance and ensuring the reliability of web applications. Best practices in web development. REST-full API design. Designing REST-full API involves adhering to principles that ensure your API is scalable, maintainable, and easy to use. REST-full API should be stateless, meaning each request from a client to a server must contain all the information needed to understand and process the request. Endpoints should be organized around resources, such as OR, using standard HTTP methods GET, POST, PUT, DELETE to perform operations. Each resource should have a unique URL, and API responses should use appropriate status codes and consistent structure, often leveraging JSON or XML formats. Documentation is also crucial, providing clear instructions on how to use the API, expected inputs and outputs, and error messages. Handling errors gracefully. Proper error handling is vital to providing a good user experience and simplifying debugging for developers. Use appropriate HTTP status codes to indicate the nature of the error, such as 400 for bad requests, 401 for unauthorized access, 404 for not found, and 500 for internal server errors. In addition to status codes, include detailed error messages that provide insight into what went wrong and how to potentially resolve the issue. Implement global error handling in your application to catch unhandled exceptions and return a standard error response. Logging errors is also important for diagnosing issues in production environments, enabling developers to address bugs and improve the system. Ensuring data integrity. Data integrity ensures that the data remains accurate, consistent, and reliable throughout its life cycle. Implement validation on both client and server sides to check for data completeness, correctness, and format compliance. Use database transactions to ensure that a series of operations either all succeed or all fail, maintaining consistency. Implement referential integrity in your database design to ensure relationships between tables are preserved. Regularly back up your data and have a strategy for restoring it in case of corruption or loss. Additionally, employ checksums or hashes to detect and prevent data corruption during transmission or storage. Securing endpoints. Securing your API endpoints is critical to protect sensitive data and prevent unauthorized access. Use HTTPS to encrypt data in transit, ensuring that it cannot be intersected or tampered with. Implement authentication mechanisms, such as OAuth, JWT, or API keys to verify the identity of users or systems interacting with your API.
Use role-based access control RBAC to restrict access to resources based on the user's role or permissions. Validate and sanitize all input to prevent injection attacks and other security vulnerabilities. Regularly update your dependencies and software to patch known vulnerabilities and stay informed about security best practices. As we conclude our deep dive into the world of HTTP and HTTPS, it's clear that mastering these protocols is crucial for any developer aiming to excel in web development. The knowledge you've gained not only empowers you to build more secure and efficient applications, but also inspires you to explore further innovations in the vast realm of internet technology. Remember, every time you open a browser or connect to a server, these protocols work tirelessly behind the scenes to ensure smooth, reliable, and secure communication.
Whether you're debugging a network issue, optimizing performance, or securing your endpoints, the insights from this exploration will be invaluable. Thank you for reading, and here's to your continued success in web development.